Hello, welcome to this video tutorial. Here we're going to be looking at conservation of energy problems. Now, these are the type of problems where you're going to see changes in energy. So, for instance, when we see one type of change in energy, such as change in potential energy or kinetic energy, then that's usually associated with work being done to transfer energy to or from that object to cause that change in energy. But when there are two or more changes in energy in a closed system, we can now use a new technique called the law of conservation of energy. And all we have to do in problems like this is indicate an initial energy and set that initial energy equal to a final energy. And that's how these problems will end up resolving themselves. Now, there will be some connection to kinematics here and there, but we'll use it as we need to use it, okay? So in this, we're going to be looking at four problems. The four problems are going to be energy on an incline, level one, energy on a vertical toss, energy of a displaced pendulum, and then finally, distance traveled projected by a spring. So we're going to have a spring-loaded mass. It's going to be fired by the spring, and it'll be moving an object on a rough surface that will eventually slow down due to friction. So let's go ahead and begin. The first question is called energy on an incline level one. And what we'll be given on this problem is we're going to be given the speed, the angle, okay, and the mu, okay, because it's going to be, well, actually, no, this is not, this is a smooth surface, okay. So let's go ahead and log in to the question. Okay, you can see we're given the speed, so go ahead and record yours. You're also given the mass of the little cart that's going up. So record everything that's given. Remember to convert from grams to kilograms instantly, right? 518 grams in my case is 0.518 kilograms. My angle appears to be 16.1 degrees. Okay. And the goal, here's what we're going to do. So using that kinetic energy, we're going to find the distance of the car. It will move up the incline. Okay. So basically, here's sort of the plan. We're given the speed. We're given V naught, which means we can find the kinetic energy. Now, we know that kinetic energy is going to transform into potential energy at the highest point. Now, since we know that potential energy equals mgh, we'll solve for height. Lastly, and you can kind of see this from my picture here, let's pretend that the cart gets this high right here. Okay, gets to that height right there. Well, you can see the triangle that's created. If that's the height, okay, then we would solve for the hypotenuse of the triangle given the height and given the angle. That's how we're going to find the distance it goes up the hill. Okay, so that's going to be our plan and our strategy for dealing with this problem. First things first, let's find how high it goes. So we're going to use, so since there are two changes in energy, we have a change we are given, okay, we see that there is a change in speed because the cart will slow down as it goes uphill. And clearly there's a change in height because you're going uphill. So change in speed, change in height. Though if I see two changes in energy, I know that I can use the law of conservation of energy. Now, the equation for it is really, really super simple. It is total initial energy equals total final energy. Now, initial energy, in case you forgot, total energy, in case you forgot, is the kinetic energy plus the potential energy. We saw this play out in our conservation of energy lab. So I'm going to rewrite E initial as KE initial plus PE initial. And I'm not going to write PEG, but just note that this is gravitational potential energy in this problem, not elastic potential energy. There's no spring in this problem. That's going to equal KE final plus PE final. Now, when you write out that equation, remember, kinetic energy is associated with motion, potential energy is associated with height or position. So you get to cancel some things. So for instance, I know I'm starting with kinetic energy, but my cart is at the lowest part of the problem. So it really starts with zero potential energy. There's no potential to fall when you're at the lowest point in the problem. Okay. Now on the final side, when it gets to its highest point, you're going to have potential energy due to its height, but the kinetic energy is going to drop to zero because the object will stop at its highest point. Okay. So that's how you can utilize this equation, and it whittles it down really nicely. Replace these equations here and here with their respective formulas. Kinetic energy equation would be 1/2 mv initial squared equals mgh. Now, you're trying to solve this equation first for height. Okay, remember our strategy. We got to solve for height, and once we solve for height, then we can figure out the distance it goes up the incline using trigonometry. Okay, we got to find the height first. So to solve for height, I'm going to divide by mg. You'll see the masses cancel on both sides, and you'll see that 2 is basically down here with the g. So if I rearrange this, I get that the height is equal to v squared divided by 2g. So I'm going to go 2.752 squared, put in your velocity and square it, over 2 times, and I just got to double check and make sure, yes, sure enough, you are given the gravitational field strength, the acceleration of the gravity on your, where your experiment is being run. So mine is 10.1. Make sure that you note what your g is. My g is 10.1 meters per second squared. Okay, don't just automatically assume it's 9.8. It won't be, okay? All right, now take a moment to put that in your calculator and get your value for the height at which this thing goes uphill. Okay, so now for me, I'm getting a height of about 0.375. 0.375 is my height. Now, what I'm trying to say is this. I'm going to draw a small picture of it. This is my theta. This is the distance I'm trying to find. I already found the height. I can use an equation for sine. Sine of theta equals opposite over hypotenuse, so h over d. And if I solve for d, I simply swap it out. So d is equal to h divided by the sine of the angle. And that's how we're going to solve for the distance. So d, how far we go uphill, is going to be whatever your height was, minus 0.375 meters, divided by the sine of whatever your angle is, minus 16.1 degrees. All right, so everyone take a moment to figure out your height, or excuse me, your distance. For me, it looks like it's going 1.35 meters up the plane. I just have to make sure what unit it's supposed to be in, and clearly it says distance in centimeters, okay? So what I'm going to do is I'm going to enter, that would be, to put it in centimeters, I got to move it 2 spaces to the right, so that's 135 centimeters is what I need to enter for my program. Okay, when you do this, it's going to run the simulation until the speed of the cart gets to 0, and you can see it's constructing kinetic potential and total energy graphs. Okay, and there you go. There you go. What you are going to do is you're going to take some time with 3 different colors, and you're going to reproduce that graph. Now, if you have the ability to copy and paste that graph right there onto your page, go ahead and do that. But I'm just gonna recreate it. It's easy enough to recreate. You can clearly see we're starting with a potential energy of about 4, around 4 joules. We have a a kinetic energy of about 4 joules, a potential energy of 0. The potential energy rises from 0 to 4, and the kinetic energy drops from 4 to 0, with the total energy being the same. So I'm going to go ahead and recreate that in the axes above. So, and this only goes, you can see it only goes for about 1 second. Okay, so I'm going to recreate this. I'm going to have my total energy like this. Okay, use whatever colors you want. Honestly, it doesn't matter. I'm going to go like this, like that, and like that. I think that's what I saw. Oops, sorry, other way, other concave, other way. So like that. Okay, the kinetic energy drops. So this is my kinetic energy. This is my total energy. And then this will be my potential energy. Okay, make sure you color code which are your 4 graphs, okay? And that's it. That's it for question number 1. Okay, energy on an incline level 1. Hopefully you were able to get this correct yourself. If so, let's move on to the second question, energy of a vertical toss. Well, as the name of the problem would suggest, you're going to toss a problem up vertically. It's going to get to its highest point, and you're going to essentially be trying to calculate and predict how high it actually goes. Okay, so let's go ahead and sign into our program. Now, note what we've been given. We have to find the total energy in joules and the maximum height in centimeters. So note everything we're given here. We're given mass, g, and the speed at which it's launched. So record all your stuff. Convert to kilograms. There we go. Sorry, it's going to drive me a little crazy. Okay, and then my speed, 6.336. It's going to be my V naught, 6.336 meters per second. Okay. So first off, let's calculate the kinetic energy of the ball right as it's leaving the table. Well, kinetic energy, in case you forgot, is a 1/2 mv squared calculation. So we're going to 1/2 times your mass in kilograms times your speed, your velocity, but you have to square that. So remember, how do we do this equation here? We're going to start with square the speed, multiply by mass, then take half. That in your calculator, I'll figure out mine, you figure out yours. All right, I'm getting about 4.01 joules. Keep in mind, what this means is the kinetic energy you start with here transforms, excuse me, into gravitational potential energy at its highest point. So this is not only the kinetic energy, it's also the gravitational potential energy that it transforms into. Okay, so it says use conservation of energy to find the maximum height your ball will reach. So I'm going to show you 2 ways to do this problem. One way is to find the energy at the initial point. We did that, okay? And then, and so I'm going to draw a line here just to kind of show the differences. So I found my initial kinetic energy, which is equal to my final potential energy. And that's what I get, 4.01, 4.01 joules. And then I solve for H. So potential energy equals mgh. Clearly, I have to divide by mg. So H would be my potential energy divided by mg, 4.01 joules over my mass, 0.200 times my g, which I forgot what it was, 6.3 in my case. Okay. Okay, I'm getting about 3.18 joules, okay, for that height. Okay, so I've got my, or 3.18 meters. I'm mixing up my units here. Sorry about that. 4.01 joules of kinetic initial potential energy, or kinetic initial energy, and then final potential energy. Now, the other way to do it is by using the law of conservation of energy equation, okay? And the way that works is we have KE initial plus PE initial equals KE final plus PE final. Well, I start with kinetic energy, but I have no potential energy. At the highest point, my kinetic energy goes to zero, but I have potential energy. Now I replace these equations, these energies with their respective equation. So the equation for this would be 1/2 mv squared. The equation for this would be mgh, and I simply solve that equation for h. Okay, now to do that, I divide by mg, and h is equal to v squared divided by 2g. So I'll take my 6.336 squared over 2 times 6.3. 2 times 6.3. Okay, so I'm going 6.336 squared over 2 times 6.3. Whoopsie, I messed it up. Okay, 6.336 squared. There we go. 2 times 6.3. That's better. Okay, so I'm getting the same thing. I'm getting 3.18 meters high. So my answers are consistent. That's how high it's going to go. And then what I'll do is I'll draw in my graph above once I put in. So let's put in my energies here and see if I was able to get this right. So my energy is about 4.01 joules. Okay, and my maximum height, I found it in meters. That would be 318 centimeters, right, is what I have to enter into the program. I have to move the decimal 2 places to the right. 18. And then what's going to happen is it's going to fire the ball to its highest point, and when it stops, when the velocity equals 0, it's going to check and see if your prediction was right. And you can see mine's a little off, but hopefully it's close enough to get the point of what we're doing. You'll get the results when it reaches the ground. And okay, so sure enough, I think I was off by a centimeter, so that's not too darn bad at all. So you can see I've got a total energy of about 4. Okay, so you're going to choose 3 colors. Doesn't matter. One for total energy, kinetic energy, and potential energy. Okay, so I like to start with total energy. Okay, so total energy of 4. And so you can see this is just for 2 seconds, okay? 2 seconds. They made it simple for us to do this. So we're going to go for, oops, I messed that up. Okay, so that's for 2 seconds. Then what we're going to do is we're going to go, and you start with no potential energy. So my next one's going to be potential energy. So this is potential energy. This is total energy. Okay, now for potential energy, I start with no potential energy. At the highest point, I get to maximum potential energy, and then it comes back down to 0 potential energy when it reaches the ground. Okay, and I'll use red for kinetic energy. I start with my kinetic energy being my total energy at 4.01 joules. At the highest point, my kinetic energy goes to 0, so you can see it's going to look like this. And then it's going to get up to its highest value when it reaches the ground again. Okay, so this value of 1 second, that would be the highest point of the graph. Okay, so that is question number 2, energy on a vertical toss. Hopefully you were able to get it right as well. All right, if so, let's move on to question 3. Question 3 is about finding the energy of a displaced pendulum. Okay, so here's what we're going to do. It's going to give us a couple things. Let me show you what those things are. Log into your question. It's going to give you a pendulum, and it's going to show you exactly where the center of the ball is. We have to measure the length down to the center of the ball, and it's going to give you the mass of the ball in grams, of course, converted to kilograms. So that's what I'm going to do first. That looks like a washer, not a ball, but we want to find to the center of that washer. Okay, so I'm going to record my values. So the mass, my length appears to be a little past 150. It's not quite 160. I'm going to go 156. I'm going to go 156. So I'm going to draw a line down to about here. That is about the center of my ball right there. Okay, length, and that's the length. The length is about 156 centimeters or 1.56 meters. Okay, now the mass we were given was, oops, wrong way. It was 319 grams. 319 grams, which of course is 0.319 kilograms. Okay, so we have everything we need. Now what's going to happen is we're going to click on the ball. I keep calling it a ball. Let's just call it a ball. It's probably a washer, but let's call it a ball. As soon as you click on the pendulum bob, the what looks like a washer to me, but I'll call it a ball, it's going to displace it to a certain angle. Now you have to record that angle and draw it on the PDF. So my angle is exactly 33 degrees. That's what it's been displaced to. So I want you to draw a line to your angle. Okay, and what I would do is I would go to shapes. They'll make it better. Go to shapes and draw a straight line from this point here to where that angle is, just like that. And then put the ball, go back to drawings, you can put the center of the ball right at that point right there. Okay, so that is what we're trying to do. Okay, center's right there. Okay, and then just record your angle. Record your angle. Oops. I didn't want that. There we go. Okay. So there's my angle. My angle is 33 degrees. Okay, now we're going to do something with this shape here because in order to figure out, we basically have potential energy right here. We have potential energy. There's no kinetic energy because the pendulum will start from rest. At the lowest point, when this thing swings through its lowest point right here, then what you're going to have is you're going to have maximum kinetic energy and you're going to have no potential energy because you can't get any lower than the lowest point of a pendulum swing. Okay, so basically all of this is going to transform into this. Okay, now in order to find potential energy, you know that potential energy is equal to mgh, the height. Well, we've got the mass. G is simple. I do want to make sure and double check and make sure this is not on some other planet. It does not tell me. Yes, it does. There we go. You have to go to the very bottom and it's going to give you your G. My G is 3 newtons per kilogram. So I'm glad I looked. So G, and my problem is 3 newtons per kilogram or meters per second squared, doesn't matter. All right, so I've got M, I've got G, and I've got to find H. Well, here's what we cannot assume. Please do not assume that H is the length of the string. That's not true. H would only be the length of the string if you release the pendulum from the highest point here. If you release the pendulum from the very top, then what happens is as it falls, it will fall a distance h, which is the same thing as the length of the string. That's only if it falls from the vertical. It's not falling from the vertical. It's falling from some displaced angle. So how do we find the height? Here's how we do it. Okay, I want you to make yourself a triangle. First of all, we're going to measure, we're going to draw a line. Go to your drawing tab. We're going to draw a dashed line that goes all the way over like this. Okay, and hopefully you guys can see the right triangle that develops there. Okay, this is still the length of your pendulum, which in my case is 1.56 meters. Okay, this whole thing here is also the length of the pendulum. Okay, you see what I'm talking about? This whole thing is the length of the pendulum, the yellow. Now, the red that I'm about to highlight, that is the height right there. The height is from where the center of the ball starts to where the center of the ball will be. That is the height. Okay? Now, how do you get that? Well, you're going to need to find this side of this triangle right there. Well, if you look carefully, that is the adjacent side of theta with a length of 1.56. So that means this side here is actually going to be the length L times the cosine of whatever your angle is, minus 33 degrees. Okay, and I'm going to highlight that one in blue. Okay, so the blue plus the red equals the yellow. Okay, let me put that again. So I'm going to get my height, or excuse me, actually, let me do that a different way. Sorry about that. The entire length, okay, I got the entire length right here. The entire length is equal to L cosine theta, that part right there, plus the height right there. Now solve this for height, you have to subtract L cosine theta. So the height would be L minus L cosine theta. At this point, I would even go so far as to factor out an L. That'll make the problem solving that much quicker. If I factor out an L, then height equals L times the quantity 1 minus cosine theta. Okay, so that's going to be our height. It's going to be the length times 1 minus the cosine of the angle. That's how we're going to figure out the height. Now, the problem is going to work like this. Let's use our conservation of energy. So I have a change in speed and a change in height. So I will use the law of conservation of energy, which tells us that energy initial equals energy final. The initial energy was potential energy. That's the initial energy I have. The final energy is kinetic energy. Now replace these with their respective equations, and we get mgh initial equals 1/2 mv squared final. And we are trying to solve this for the speed. Thank you. There we go. The speed at the bottom of the swing. So that's what we're solving for is v. Now, in order to solve for v, we have to get rid of the half, the m, and the square. So we'll start by multiplying by 2. There goes the half. When you divide by mass, it divides both sides. This is mass independent, which is nice. And then all you have to do is square root. So I get v is equal to the square root of 2gh. But remember, what was h? H was L, oh, so I put it over here, L times the quantity 1 minus cosine theta. So I would rewrite this as 2g L times 1 minus cosine of my angle. If this went a little too fast for you, you might want to pause and rewind the video and watch it about 5 or 10 times until it starts to kind of sink in a little better. But at this point, go ahead and plug in your numbers. Okay, so 2 times whatever your g is, minus 3, times whatever your length is, minus 1.56, times 1 minus the cosine of whatever your angle is, minus 33. Okay, put that in your calculator. And when you're done with that, now I'm getting 1.51. Don't forget to actually square root. Okay, which means I'm getting about 1.23 meters per second for that right there. Okay, so I did kind of all of that up here. The other way you can do this problem is to find the potential energy. The potential energy at the top is equal to the kinetic energy at the bottom, and then you're solving the kinetic energy equation for speed. It's the same thing. Multiply by 2, divide by mass, and square root. So speed would be 2 times the kinetic energy divided by the mass, and then square root that. But you'd have to find the potential energy still using the same thing, right? The potential energy would be mg times L times the quantity 1 minus cosine theta. So you still have to find it the same way. All right, let's see how we did. Energy-wise, let's see. Energy-wise, well, I got to calculate the energy. It's asking me to, so I'm just going to calculate the kinetic energy at the bottom since I've got the speed calculated. So 1/2 mv squared is going to be 1/2 times Gosh, I forgot my mass. 0.319. So 0.319 times my velocity, 1.23 squared. Just note that's going to be my kinetic energy at the bottom, and it's going to be my potential energy at the top. It's going to be both, right? The potential energy at one point is the kinetic energy at the other point. So I'm going to go 1.23. I'm going to square that. I'm going to multiply that times 0.319, and then I'm going to take half. And I'm getting about 0.241 joules. So I'm going to enter in my values, see how I did. In joules, and it's like I got a speed of 1.23. It's going to fall to the lowest point, and it will check your work, and it looks like my work was right on. Okay, so hopefully you were able to get question number 3, energy of a displaced pendulum, correct as well. Okay, well, if you're able to get this right, then it's on to our final question, number 4, distance traveled projected by a spring. Now, here's what we're gonna do. We're gonna write in the mass of the spring. We're gonna write in the spring constant, not the mass of the spring. I'm sorry. We're gonna write the mass that's getting pushed by the spring. We're gonna write the distance the spring is compressed, the spring constant, all of that. We're gonna write the mu because we're gonna be given the coefficient of friction, okay, on the tabletop, and we've got a lot of things we got to find. Okay, so here we go. Let's go ahead and get into this problem. First, go ahead and sign into your problem, okay? And then start copying down your information. So my K, my spring constant, is 44.1. Newtons per meter. My mass is 48 grams. Please note, 48 grams would be 0.048 kilograms. Remember to move your decimal 3 places to the left, okay? And then you're going to get your compression distance. Mine is 85 millimeters. So 85 millimeters. That means that's going to be X. So 85 millimeters. Remember to go from millimeters to meters, you got to go up 3 stairs. That moves the decimal 3 places to the left, or 0.085 meters. So just take a second to change all of your stuff into kilograms, meters, and you'll be good to go. So show the calculations for the energy stored in the spring. Well, the elastic potential energy equation is 1/2 K x squared. So 1/2 times your K minus 44.1 times X 0.085 squared. Figure out this is your initial energy. So this is going to be your initial energy in the problem. Okay. Let's figure that out. All right. So you can find that, and then you can find the speed, assuming all the stored energy turns into kinetic energy. So once you find that, that's also going to be the kinetic energy of the block, okay? And you can find the speed. Now I'm going to show you a second way to do this problem, okay? Because one way is kinetic energy equals 1/2 mv squared, solve for speed, multiply by 2, divide by mass, square root. Okay, but it requires 2 equations. Find this, and then a second equation to find that. Okay, so I'll show you a second way to do this in a moment. For now, let's just finish this first way and make sure we can understand how to do this one way. So we're going to go 0.085, well, whatever your spring compression is, square it times your spring constant, and then take half. And so I'm looking at 0.159 joules. Okay, I'm going to go 2 times 0.159 joules divided by the mass of 0.048 times 2 divided by 0.048 square root. I'm looking at about 2.58 meters per second. So that's going to be my speed right there. Okay, it's not only the speed, it's going to be the initial speed of the problem. You're going to see in a moment. This problem has a lot going on here. This is a conservation of energy problem to go from here to here, where all of your elastic potential energy has transformed into kinetic energy, which is 1/2 mv squared. And then, of course, from this, we're finding our speed. But our speed is actually our initial velocity of a constant acceleration problem. Now, then we're going to use Newton's law, specifically Newton's second law, net force, right? Causing force minus opposing force equals ma to solve for A, right? And then we're going to use constant acceleration to find, I believe we have to find the time. Yes, find the time and the distance it takes to stop. So we have some kinematic stuff we got to do. We have some constant acceleration stuff. To find the time, it might be easy because that's just going to be v equals v naught plus at. You know the final speed is 0. You could solve for time. Okay, that's easy. And then you can use delta x equals v plus v naught over 2 times t. You know this comes to 0. And that'll help you find out how far it went. So you got some constant acceleration equations you can use to help you find what you need to at the end of the problem. But for starters, we got to find the speed. We did that. Now, the other way to do this is to use conservation of energy as a whole in one step. So we have a change in spring and a change in speed, and conservation of energy would tell us that all the initial energy transforms all into the final energy. Well, the initial energy is 1/2 kx squared. Okay, it's the elastic potential energy, and that's going to convert into kinetic energy right off the spring. Okay, so this becomes 1/2 kx squared equals 1/2 mv squared. Okay, now you can clearly see that if I'm trying to solve for speed, I will multiply by 2, and you can see the 1/2s cancel from both sides. Divide by mass, and then square root. So what I get is I get v equals the square root of kx squared divided by the mass, and then I have to square root. So k was, I forgot, 44.1, okay, times x, which is 0.085 squared divided by the mass, which was 0.048, and then I square root that. Okay, so we're going to go 0.085 squared times 44.1 divided by 0.048. Square root that, and sure enough, I'm getting the same speed, 2.58 meters per second. But I like using this, and this is what we're going to start kind of working towards, is a more efficient way to use conservation of energy. That's the way I'm going to start showing it from this point on. But just note, you do have options in terms of how you can relate the information. You can always find the energy at one point and just equal it to the energy at another point, and then use that energy to solve for a variable within that contains that energy. So that would be another way to do it. It's a little bit longer. It requires 2 equations and twice the solving, but still that is very useful for a lot of students. Okay, now comes the Newton's second law part. Okay, why do I say that? Because we got to find acceleration in order to do constant acceleration here. Okay. So the first step 4 is all about the free body diagram. So if you look at the forces, you would have the weight balancing the normal force, and then you'd have friction, which is equal to mu times normal force. So normal force equals mg, and friction equals mu times normal force. Keep in mind, the object is moving to the right, but it's slowing down. That means the acceleration is going opposite the motion when you slow down, which means friction is the causing force. Okay, so if I use my Newton's second law equation, tells us causing force minus opposing force equals ma. Well, my causing force is friction. I do not have an opposing force because nothing is going this way, opposite the acceleration. So I can cancel this, and I just divide by mass to solve for acceleration. So my force, my causing force is mu times normal force, that's friction, divided by mass. But that's the same thing as mu times mg. Remember, normal force is balancing the weight. and that's divided by m. And you can see that cancels. That's just going to be a simple mu times g calculation. That's how you're going to find the acceleration. Mu, I don't even know if I recorded my mu. I did not. I did not record my mu. So make sure you record yours. Mine is 0.19. 0.19. So mu is 0.19. I'm going to use it in my calculation now. 0.19. I need to take a look and make sure that my g is given in the problem because I can't assume it's going to be 9.8. So I better look. Let's see. Do not see. I do not see anything for G telling me it's anything other than 9.8. So I'm going to go ahead and use that. Yeah, I'll go ahead and use 9.8. Okay, so we're going to go 0.19 times 9.8, about 1.86 meters per second squared. That's my acceleration. Now we're going to find the time and distance. Okay, so I'm going to split this into two parts. They're constant acceleration all the way. Remember, what are our variables? Delta x, v, v naught, a, which you just found. Mine's 1.86 meters per second squared. And you're looking for time. You're looking for time, and you're looking for how far? Displacement. We know that this is coming to 0 because you're stopping, and we know the initial speed v naught, that's the speed you calculated right here. Okay, in my case, 2.58. So you got all the information you need. You just need to plug it in right and choose the right equations. As I mentioned earlier, if you look at the combination of data here, I can find time using equation 8, v equals v naught plus at. That's 0. And if I subtract v naught and divide by time, time is equal to negative v naught divided by a. So negative 2.58 meters per second over negative 1.86 meters per second squared. So why am I putting in a negative acceleration there? Well, remember, what is the object doing? It's going forward, but slowing down. That's negative constant acceleration. These cancel, of course, giving you a time in which the object will come to rest. So 2.58 divided by 1.86. And in my case, I'm getting 1.39 seconds that it takes to do this. But then I'm going to come back with probably equation number 11, v plus v naught over 2 times t. We come to rest. So this is going to be equal to v naught times t divided by 2, which would be 2.58 times the time you just found. Mine was 1.39. Then take half of that. So that times 2.58 by 2, about 1.79. So I have to double check. It's 1.79 meters, but I'm fairly certain I have to express it. No, okay, so we are supposed to express our distance in meters. I had to double check because sometimes we have to express it in centimeters. So I'm going to put in my answers. Okay, my time, 1.39 seconds. Okay, and my distance, 1.79 seconds. All right, and there you go. There you go. So this one was a little more involved because this was all of our concepts combined into one, right? It's our conservation of energy that we're currently learning and practicing. It was our Newton's second law from last unit, and then it was our constant acceleration from way back in August when we first began. It was all three of them in the same problem. Okay. Now there is another way to solve this problem, even a little bit more simpler than I did here, using what's called work energy theorem. But for now, we're going to make this satisfactory as far as a solution. Okay. All right. Well, I hope you were able to be successful in your problem solving. If you had any trouble, please make sure that you come and see me. All right. Until next time, we'll see you.